Okay, so in the previous sections in 11.8 and 11.9, we've been dealing with power series in general, and our segue into it was the function 1 over 1 minus x, because of its similarity to the formula that we have for finding the sum of infinite geometric series. And we recognize the fact that that was, 1 plus x squared plus x cubed plus, whatever. And it's, n is equal to 0 to infinity of x to the n. And, then we took those and we found other ones by manipulating it. But here's the thing, we don't have to use this particular function and this power series as a jumping off point for everything. There is actually a more general form, and it comes to us by way of derivatives. Okay? So let's say that we have some function, and we'll call it f of x. Okay? Well, f of x is, some representation, some expression in terms of x. Well, if there is a power series that can represent that function, then we know that it's, a sub 0 plus a sub 1 x to the first plus a sub 2 x squared plus a sub 3 x cubed, and on and on and on, where, a sub whatever just happens to be the particular coefficient, and then of course that coefficient can take any form. So if you are capable of constructing a power series, then obviously there's going to be some discernible pattern. But in order for that power series to actually be equal to f, we know that not only does it have to be equal to f at every point, its first derivative has to be the same at every point. So its slope has to be the same at every point. Its concavity, its second derivative, has to be equal at every point. Its third derivative. So basically, not only does the function have to be equal to the power series output at every single point, so do all of its derivatives. Okay, and that's basically the way that we enter into what are called Taylor and Maclaurin series. Okay, and so what you have here is, obviously a sub 0 is a constant, so it falls out, and what you have is a sub 1. And if you take the derivative of this term, you bring the 2 down, 2 a sub 2 x to the first. You bring the 3 down, 3 a sub 3 x squared plus dot 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 dot. And what you have here is this one had sort of an a sub n x to the n term, right? Well, then you have n times a sub n x to the n minus 1. Okay, well, let's take the second derivative. And it's, and now that's a constant. It doesn't have any variable that it's attached to. So what we have is 2a2. Okay, but now this one, the 2 needs to be brought down and combined with that 3, and you get 6 a3 x to the first. The next one was going to be 4 a sub 4 x cubed, so it becomes 12 a sub 4 x squared. The next one was going to be 5 a sub 5 x to the fourth, and of course 5 and 4 makes 20 a sub 5 x to the third plus dot 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 dot. Well, you've done it twice, so you have to bring down, for this general term right here, you have to bring down the n minus 1, and you have a sub n x to the n minus 2. Okay, let's take the third derivative. Well, this, again, constant, because there's no variable attached to it. So our new constant term, once we take the derivative, is 6a cubed. 6a sub 3. This one becomes 24 a sub 4 x. This one becomes 60 a sub 5 x squared. And this becomes n minus 1, n minus 2, a sub n x to the n minus 3, So if you're keeping track of this, let's actually start talking about these leading coefficients once we take the fourth derivative. By the way, if you take the fourth derivative, once you get to 3 hash marks, you start putting a number in parentheses, superscript to the f, and that designates the fourth derivative. So that becomes 24 a sub 4 plus, and then this one becomes 120 a sub 5x plus, plus n minus 1, n minus 2, bring down the n minus 3, and we have a sub n times x to the n minus 4. And that's going to keep happening. Well, what is that becoming? Well, the whole clue to this is the fact that what does this succession of numbers look like? 0, 1, 2, 6, 24. Well, what's the next leading coefficient going to be if I take the fifth derivative? Well, that's going to wind up being 120 a sub 5, right? Well, at this point, once you get to about 120, you should recognize the fact that these are the succession of factorials. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, okay? And the fact that those are spitting out factorials shouldn't really be all that surprising. Let's go ahead and just take a look at, if you take successive derivatives of x to the fifth, y prime is equal to 5 times x to the fourth, y double prime is equal to 5 times 4 times x cubed, and we're not going to combine them, we're just going to go ahead and keep stringing them along in this factored form. Well, 5 times 4 times 3 times 2 times x, and what is the fifth derivative? 5 times 4 times 3 times 2 times 1 times, x to the 0. Oh, sorry. Well, that's 5 factorial. And if I were to start off with x to the 6th, what would its sixth derivative be? 6 factorial. Well, x to the seventh derivative is 7 factorial. X to the eighth derivative is 8 factorial, okay? Well, that's going to come in handy here in just a moment. So let's actually, instead of just doing this in the abstract, let's actually do it for a particular function, okay? Let's say, let's basically start with the hypothesis that sine x has a power series that can be derived, okay? And we're going to start off with a sub 0, a sub 1 x to the first, a sub 2 x squared, and on and on and on, plus a sub n x to the n, and of course it goes off to infinity, right? Well, what is f of 0? Because if I'm dealing with this, and I'm dealing with the power series in that form, I'm worried about sine not at any value. I'm worried about sine's equivalence when it's centered at 0, right? Because that's x, not x minus 2. If it were x minus 2, it wouldn't be centered at 0, it'd be centered at 2. So we're going to start off with this in terms of it being centered at 0, just to make the arithmetic easier, and then we can extrapolate to power series centered at other numbers. So if we do this, we know that sine of 0 has a particular value, and if you plug in 0 here, you get sine of 0. If you plug in 0 here into this infinite polynomial, the only thing left is a sub 0, right? Well, that tells me that a sub 0 is equal to 0. Okay, well that's kind of nice. We'll sort of group that together. Let's go ahead and take the first derivative. And that, of course, is going to be cosine. Well, if I happen to take the derivative of that infinite polynomial, that is a constant. It becomes 0. And I'm left with a sub 1 plus 2 a sub 2x plus 3 a sub 3x squared plus plus n times a sub n x to the n minus 1. Well, let's go ahead and evaluate the derivative at 0. And I know that if I do this infinite polynomial, plugging in 0 for x, all of the x terms fall out. The only thing that's left is the constant term. And I happen to know that a sub 1 is equal to 1, because cosine of 0 is 1. Now remember, when you take successive derivatives of sine or cosine, it's going to flip back and forth between sine and cosine, changing sign, S-I-G-N, every couple of ones, right? So it's going to go sine, cosine, negative cosine, sine, cosine, negative cosine, as it goes through. I mean, there's definitely a process. So that means that every other one is going to be 0. Right? Because when you plug in 0 for x on the right-hand side, all the x terms fall out, and you're left with a constant. You plug in 0 on the left, and it's sine, it's going to be 0. So the constant's going to be equal to 0. Well, let's go ahead and actually show that. So we have negative sine x, and that becomes 2a sub 2 plus, well, let's take the derivative of this particular term. That becomes 6a sub 3x. Okay, plus, plus n times n minus 1 times a sub n x to the n minus 2, and, that can keep going off to infinity. Let's go ahead and evaluate both of those, both the left side and the right side at 0. Well, that tells me that a sub 2 is equal to 0. Okay, well, now I'm getting somewhere, okay? Because all of these can be plugged back into the original, right? You're actually just solving for those coefficients by just taking successive derivatives and plugging in the centering value. Okay, and let's take the third derivative. Well, we know that that winds up being negative cosine x, and that's going to wind up being, obviously, the derivative of this first term is 0. The derivative of the second term, since it's just a coefficient times x, is just the coefficient, and we wind up getting the next one is going to be 24 a sub 4 x plus plus n times n minus 1 times n minus 2 times a sub n x to the n minus 3, and of course that keeps going off to infinity. Well, let's evaluate this one at 0. So we're using the successive derivatives and plugging in for that centering point in order to find the coefficients. And it's a very efficient way of doing it. And that winds up being negative cosine of 0, 6a sub 3. So that tells me that a sub 3 is equal to negative 1/6. Well, I'm not going to keep you in suspense, okay? A sub 4 is going to be 0. A sub 5 is going to be, well, let's actually try and figure this out. It's going to be positive 1 over 120. And there's a reason for that, okay? Because remember, when I take successive derivatives of a to the fifth, its fifth derivative is 5 factorial. If I take, and of course, what is 120? That's 5 factorial. If I take successive derivatives of x to the sixth, it's going to be 6 factorial, but it's going to be equal to 0, so it's 0. I take successive derivatives of x to the seventh, it's going to be 7 factorial, so it's going to be negative 1 over 7 factorial, okay? And it's changing sign because this pattern is going to persist. Sine, cosine, negative cosine. The next one is going to be sine, cosine, negative cosine, sine, cosine, negative cosine, over and over and over and over again. So that's why the signs, S-I-G-N, are going to be flipping, okay? So really what we have here is we recognize that once we start plugging these values back in for the coefficients of the original power series, what we get here is we get, well, a sub 0 is 0. A sub 1 is 1. A sub 2 is 0. A sub 3 is negative 1/6. A sub 4 is 0. A sub 5, so let's go ahead and x to the fourth. A sub 5 is 1 over 120 x to the fifth, and it goes on and on and on. Well, let's get rid of the let's get rid of the 0 terms, right? I mean, those are just kind of pointless to actually keep listing out. And what I get here is x minus 1/6 x to the third plus 1 over 120 x to the fifth minus, and let's go ahead and start doing it in terms of factorial because that's just much more efficient, plus 1 over 9 factorial x to the ninth. Well, oh my gosh, that is a pattern right there. And if it's a pattern, then I can actually list it out in sigma notation. And what I get here is I get sigma n is equal to 0 to the infinity. It's an alternating series, so it's -1 to the n. Now remember, each term, this is to the first power, third power, fifth power. So you have to jump up by 2 degrees each term. Okay, so you get x to the 2n plus 1, and of course that denominator needs to be that same number factorial, right? X to the 7th with 7 factorial in the denominator. X to the 9th with 9 factorial in the denominator. My friends, you have just found the power series that is associated with sine x. Now, does this work for all functions that actually have a power series associated with it? And the answer is yes, okay? So let's go ahead and let's take a look at what is called a Taylor series generated by f at x is equal to 0. Well, let's look at the Maclaurin, because the difference between Taylor and Maclaurin is Taylor series can be centered anywhere. A Maclaurin series is a Taylor series centered at 0. Okay? So what we know here is that if we have a function and we have the Taylor series centered at 0, we have f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial, and on and on and on and on and on. Now, you can go ahead and rewrite that, since obviously the factorial and the successive derivatives are going to form the coefficient. You can put the derivative over that factorial and leave the x to the whatever power by itself. The third derivative at 0 over 3 factorial, x cubed. The fourth derivative at 0 over 4 factorial, x to the fourth, and on and on and on and on and on. Okay? So the function that you're trying to find the Taylor series, or in this case the Maclaurin series of, winds up being sigma n is equal to 0 to infinity of f to the nth derivative at 0 over n factorial times x to the nth. Now, this is what is called a Maclaurin series. All we have to do in order to extrapolate out and talk about Taylor series is Taylor series are simply Maclaurin series that are not necessarily centered at 0. So what we have here is we have, instead of f of 0, f of a. And then not f prime of 0, but f prime of a, not times x, but times x minus a. And then f double prime of a over 2 factorial, x minus a squared. And then f triple prime of a over 3 factorial, x minus a cubed, and on and on and on and on and on. And all this is taking the previous method that I just showed you, whereby we found the power series for sine x, and it's just making it into a general formula, okay? And therefore what we have here is n is equal to 0 to infinity of the nth derivative at a over n factorial of x minus a to the n. Okay, now those may look the same, and basically they really are. This is referred to as a Taylor series, and this over here is referred to as Maclaurin. Okay, so Maclaurin is just a specific case of the Taylor series where it happens to be centered at 0. And using this, you can find the power series for a whole host of different functions. Now, sine x, cosine x, e to the x, and things like that, you're going to actually wind up probably memorizing because they happen so commonly. And then, of course, from there, we can actually move on to, once those power series are known, We can then move on to manipulating and deriving other power series from those, and not simply from our friend, the sort of geometric series, the geometric power series segue that we sort of used to enter into that discussion in the first place. So if you know, like we do, that sine x happens to be equal to what? Happens to be equal to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus dot 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 dot. What is x times sine x? Well, it's just you take an x and you just distribute it across this infinite polynomial, and that shouldn't really be that big of a deal, right? And remember that this was sigma, n is equal to 0 to infinity, of negative 1 x to the 2n plus 1 over 2n plus 1 factorial. Well, once you multiply it through by x, and you actually get, x squared minus 1 over 3 factorial x to the fourth plus 1 over 5 factorial x to the sixth minus 1 over 7 factorial x to the eighth plus dot 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 dot. What you get here is you just simply multiply this original, sorry, that's supposed to be to the n right there, negative 1 to the n, x to the 2n plus 2, because all you did was just supply an extra x. Okay, so that's how we're sort of going to move forward from here. Taylor Maclaurin allows us to find the power series associated with a whole host of different functions, and from there, basically, there's an explosion of what we can do in terms of the representation of functions using these power series. Okay. Now we've gone way over our usual length of time for any particular video, so I'm going to go and call it quits now. In future videos, we're going to be basically just doing further examples, and I'm going to show you not only sine, but cosine and e to the x and a couple of other common power series. We're going to talk about not only how to derive the power series, but how to derive a truncated, sort of a shortened version of these, which are called Taylor polynomials rather than Taylor series. And the Taylor polynomials are used not to mimic exactly the values, but to approximate. And of course, anytime you approximate, basically what enters in is a discussion of remainder and error calculations, as in how good is this approximation. So that's kind of where we're going from here, and sort of the trajectory that's mapped out for the rest of this section 1110. This section is kind of complicated, but is extremely important, so we're going to make sure that we don't shortchange ourselves in terms of covering this material and covering it well. As always, if you have any questions, please do email me. Bye.